Back to the correspondence that we made between polarization and spin. Okay, the classical case of polarization and the quantum mechanical case of spin. Okay, so we said that we can we can suggest a correspondence like this. Sz plus can be related to the x polarized light and Sz minus to the y polarized light. Similarly, Sx plus to the x prime polarized light and Sx minus to the y prime polarized light. Okay, now let's try to apply this correspondence and try to go a little bit forward. Okay, so what we see in the experiments is this. As I said before, let's first write the case of polarization. I've got an X filter here. Okay, there's no Y component, and then it goes to an X prime filter. This is an X filter, this is an X prime filter, and what do I get? I see that it has both X component and Y component. All right. Now, what was the reason for this? We said that the X prime direction can be written as a linear combination of both X and Y directions. That's the reason. X prime has a component along X direction and X prime has a component also along Y direction. Okay, so we expanded X prime in terms of X and Y, and this explained why these things are happening. All right, now let's look at the Stern-Gerlach experiment. We had we had atoms, and first we had what we called an Sz plus filter. Okay, Sz plus filter. Now I subject it to an Sx plus filter, Sx plus or Sx minus filter, and then I see that it picks up. Here there's only Sz plus component, but now it picks up both Sz plus and Sz minus. Okay, so this means that maybe this Sx plus, okay, the atoms which are characterized by Sx plus is some sort of a vector which can be written as a combination of a vector corresponding to Sz plus and a vector corresponding to Sz minus. All right, because here we exactly had that. We had x prime as a vector, x prime which was a vector, and it had components both in the x direction and the y direction. All right, so maybe we can assign some sort of vectors. All right, not the exact vectors that we talked about before, but some mathematical objects that behaves like this to describe this kind of behavior, because they look very similar. Right? They look very similar. All right. So the correspondence suggests that we might be able to represent the spin state of a silver atom by some kind of a vector, all right, in new kind of two-dimensional vector space. All right, it's not the exact physical space that we are familiar with, for reasons that will become clearer as we move on. All right, so let's say that there is some abstract vector space which should not be confused with the usual two-dimensional space. All right, it's also a vector space. These are objects that behave just like the two-dimensional vectors in the xy plane, but they live in a different kind of space. They live in a different kind of space. Okay, these are not, for example, these vectors represent spin states in the two-dimensional abstract space. The vectors represent spin states. Okay, so this is not the actual two-dimensional xy plane. Okay, now when we discussed the case of polarization, we saw that x hat and y hat are the base vectors used to decompose the polarization vector x prime of the x prime polarized light. This is exactly what we did. We decomposed x prime in terms of the base vectors x hat and y hat. Okay. Similarly, it is reasonable to represent the Sx plus state by a vector. Okay, we made the correspondence between x prime and Sx plus. Okay, so maybe we can represent, just like the x prime polarization obeys the logic of vectors, maybe corresponding to the Sx plus state. This was the correspondence that we made. So maybe we can use some sort of a vector to represent the Sx plus state, okay, which we call a ket in the Dirac notation. Right? These vectors, these are not usual vectors, we'll call them as kets. Okay, this kind of notation is called the Dirac notation. Now we'll develop this fully in the next section, but this is the basic idea. Right? So the vectors that we'll use in order to differentiate from the usual real space vectors, we'll call them as kets. Okay, so it is reasonable to represent the Sx plus state by a vector which we call a ket. Okay, for now this is just a name. Right? These vectors are called kets. That's all. Okay. Now we denote this vector by a symbol, all right? So we need, in the case of polarization, we use this hat and prime or vector signs, etc. All right, here we'll use simply, in order to denote vectors associated with these spin states, we'll denote it in these angled brackets. Okay, this is just a notation for now. Okay, so Sx plus this symbol is called a ket. Okay, this you can call as ket Sx plus. All right, so the ket Sx plus is some sort of a vector that lives in a different kind of abstract space, and it represents the spin state. Okay, it represents the spin state Sx plus. Okay, so we denote the vector by ket Sx plus and write it as a linear combination of two base vectors Sz plus and Sz minus. Okay, here we wrote x prime in terms of two basis vectors x and y, and we made the correspondence x prime corresponds to Sx plus, x corresponds to Sz plus, and y corresponds to Sz minus. So just as we wrote x prime as a linear combination of x and y, making use of the correspondence, we can, so let me write it clearly here. We have this x prime, we wrote it as a linear combination of x hat and y hat. Okay, and the correspondence that we suspected said that maybe there are these vectors Sx plus, because x prime corresponds to Sx plus, which can be written as 1 by root 2. Here x polarization, we said that it corresponds to Sz plus in our analogy, plus 1 by root 2 Sz minus. Maybe we can do this. Okay, so we denote this vector using these angled brackets. Okay, so this is what we are suggesting now. Maybe we can do this, right? And then it will somehow explain why, after passing through an Sx plus filter, all right, it picks up an Sz minus component, because Sx plus in this notation, the Sx plus vector has a component both along the Sz plus direction and along the Sz minus direction. All right, so the word direction I use here in an abstract sense. All right, it's not an actual direction in space, it's an abstract direction in some abstract space. Okay. Similarly, the same logic goes here. We make use of the correspondence to write Sx minus. Can this be written as minus 1 by root 2 Sz plus, because in that other case we had y prime is equal to minus 1 by root 2 x hat plus 1 by root 2 y hat. Okay, so applying the correspondence, maybe we can write this Sx minus as minus 1 by root 2 Sz plus 1 by root 2 Sz minus. All right, now this is, for example, this is just a motivation. All right, we are just looking at the similar kind of behavior and trying to explain or describe these things using similar kind of mathematical objects. All right, but later when we study quantum mechanics, when we go deep into them, when we go into the mathematical formulation, we'll show how to obtain these expressions, okay, from starting from the basic ideas of quantum mechanics. All right, so maybe we can do this. All right, so the unblocked component coming out of the, so we can say that the unblocked component coming out of the second apparatus is to be regarded as a superposition of Sz plus and Sz minus in the following sense. Okay, so now this explains it somewhat, right? Now this explains it. This is only Sz plus beam. All right, now this is an Sx plus beam. All right, this Sx plus beam has components along Sz plus direction and Sz minus direction. All right, so maybe we can write it as a superposition Sx plus equal to 1 by root 2 Sz plus plus 1 by root 2 Sz minus. Okay, we see that Sx plus has component in Sz plus direction and Sz minus direction. That is the reason why it picks up an extra Sz minus component. Okay, all right. Now all that looks well and good, but there's one more question to be answered. Okay, how are we going to represent the Sy plus minus states? There are also states corresponding to a spin along the y-axis. Right, you could put the magnetic field along the y-axis as well. Right, and then we'll get two spin states, Sy plus minus. Okay, obviously there's nothing special about x or y states, or x or y or z directions. Okay, this is just a choice of our coordinate system. So all these arguments that we had before should be applicable also in the case of Sy plus minus states. Okay, for example, if we have an Sz plus beam, okay, and we subject it to an Sg z hat apparatus, we see that there is only one output. Okay, there is only Sz plus output. There is no Sz minus output. All right. So if I take this Sz plus beam, now if I subject it to an Sgy hat apparatus, all right, there will be an Sy plus beam and an Sy minus beam. All right. So I am just changing x in our previous examples to y here. Okay, there's no specific reason. There's no preferred direction, right? There's no preferred direction like x, y, or z. These are our choices of coordinate systems. So if some of the arguments are true in the case of x direction, they should be true also in the case of y direction. Right? Now again, if I block this, and then subject this to an SGZ hat apparatus, what do I expect based on our uh, arguments before? I expect that there should be an SZ plus beam and an SZ minus beam. Okay, now if our correspondence is correct, all right, we said that maybe all these things can be described by stating that Sx plus can be written as a superposition of some sort of abstract vectors like this 1 by root 2 Sz minus. Similarly for Sx minus also. Okay, maybe I can write this Sx minus is 1 by root 2 Sz, so it was minus 1 by root 2 Sz plus 1 by root 2 Sz minus. Okay, but by doing this, we have completely made use of the correspondence that we have already made. Okay, we completely use the correspondence. Okay, now how do we represent it? Seems that Sy plus also has components along Sz plus and Sz minus directions in some sense. Okay, so we should be able to write something like, based on this logic, we should be able to write something like Sy plus is equal to some coefficient multiplied by Sz plus some other coefficient multiplied by Sz minus, etc. And Sy minus state, maybe we should be able to write this as some other coefficient or equal the same coefficient or slightly different coefficient plus d Sz minus. This is what we expect based on this. All right. But by writing these things, we have completely used the correspondence that we made. So how do we accommodate the Sy plus Sy minus states in the same scheme? How do we do this? Again, an analogy with polarized light saves us. Okay, so the idea is that we look at a circularly polarized beam of light. Okay, let's first see how we represent a circularly polarized beam of light. Okay, so this is how you represent a circularly polarized beam of light. It also has an x component or an x polarized beam and a y polarized beam. Right, so you can write it as a combination of an x polarized beam and a y polarized beam. The only thing to note is that the y polarized beam is 90-degree out of phase with the x polarized beam. Okay, all right, so it's again a right circularly polarized light is again a linear combination of an x polarized light and a y polarized light. The only thing is that the oscillation of the electric field for the y polarized component is 90-degree out of phase with that of the x polarized component. Okay, so that the oscillations are 90-degree out of phase. Now due to this, if you are looking at a circularly polarized light approaching you, you will see that the polarization vector actually rotates. Okay, that's why we call it as a circularly polarized light due to this phase difference. Okay, all right, now maybe we can write it in terms of complex notation, using complex notation. So let's write this in terms of complex notation. Let's write E vector divided by E0. This is 1 by root 2 x hat, and this cos kz minus omega t is nothing but the real part of this complex function e raised to I kz minus omega t. Okay, fine. Plus here we have got 1 by root 2 y hat. Again, this cos kz minus omega t plus pi by 2 is the real part of e raised to I e raised to I kz minus omega t plus pi by 2. All right. Now you see that this E vector divided by E0 can be written as a real part of a complex function. It can be written as a real part of a complex function. So this I write it as 1 by root 2. Okay, I'll write this as this is equal to the real part of complex vector. Actually, we'll write it as the epsilon vector. Okay, this is a complex vector, the real part of epsilon vector. What is epsilon vector? Epsilon vector is this complex vector which is given by 1 by root 2 x hat e raised to I kz minus omega t plus 1 by root 2 y hat e raised to I kz minus omega t plus pi by 2. Alright. Now this e raised to I pi by 2 is actually e raised to I pi by 2 is cos pi by 2 plus I sin pi by 2, which is equal to I. Alright, so we can write this e raised to I pi by 2 as I, and then the epsilon vector becomes 1 by root 2 x hat e raised to I kz minus omega t plus I by 2 y hat e raised to I kz minus omega t. Alright, we have made use of the fact that I is equal to e raised to I pi by 2. Alright. Okay, now we can make the following analogy with the spin states of the silver atoms, because we see that there are some other coefficients other than what we have already used. Okay, there are extra coefficients appearing here in terms of this complex or imaginary I. Okay, so we can make use of this fact to find the following correspondence. Okay, the Sy plus atom can be represented by a right circularly polarized beam, or you can find a correspondence with the right circularly polarized beam, and Sy minus atom with a left circularly polarized beam. All right, so the difference between this right circularly polarized beam and left circularly polarized beam would be that instead of a plus pi by 2 here, you would have a minus pi by 2 for a left circularly polarized beam. Okay. All right, so this is the correspondence that we make, and Sy plus atom is analogous to a right circularly polarized beam, and the Sy minus atom to a left circularly polarized beam. Okay. Now, if you make use of this analogy, we see that we are allowed to make the coefficient complex. All right. If you are making use of this, if you are using this equation, we just have to make the coefficient complex. All right. If these are real, if you are only taking the real part, then we don't have much to work on. But if you are just using it in the complex case, and if you allow these coefficients to be complex, all right, these coefficients, if you allow these coefficients to be complex, okay, there's no difficulty in accommodating the Sy plus minus atoms in our vector space formalism. That's what we do. We are making the suggestion that maybe Sy plus minus can be written as 1 by root 2 Sz plus or minus I divided by root 2 Sz minus. Okay. All right. If there's no I here, then we don't have much to work on. So if it is true that there is some sort of abstract vector space that we are using, and if it is true that this correspondence somehow works, then we have to make this extra prediction that the abstract vector space is also complex. Okay, when I say that the abstract vector space is complex, what I mean is that we allow these expansion coefficients. These are called the expansion coefficients if these are like base vectors. Okay, these are called the expansion coefficients, and we allow these expansion coefficients to be complex. Okay, if we do that, there's no difficulty in accommodating the Sy plus minus atoms also. Okay. So we thus see that the two-dimensional vector space needed to describe the spin states of silver atoms must be a complex vector space. Okay, it seems to obey the logic of vectors fine, but in addition, it also has to be a complex vector space. All right. So an arbitrary vector in the vector space is written as a linear combination of base vectors Sz plus minus, okay, with complex coefficients. The coefficients can be complex in general. They could be real, but they can also be complex. Okay. So again, we have never talked about photons. We have completely ignored the quantum aspect of light. We know that light also obeys the rules of quantum mechanics, but we have ignored that fact. Okay, we did not mention anywhere about the polarization states of a photon, etc. The analogy we worked out is between kets in abstract vector space that describes the spin states of individual atoms with the polarization vectors of the classical electromagnetic field. All right. So what we have here, the analogy that we worked out is between, we have got kets that represent spin states of atoms, okay, with the polarization vectors corresponding to classical electromagnetic field. Classical electromagnetic field. Okay. Now we could have made the analogy even more vivid by introducing a photon concept. Okay, of course, by introducing the photon concept, which is the quantum mechanical, which is the quantum mechanical counterpart of the classical electromagnetic field. Okay, we don't need it. All right, so it is not needed here. So without even talking about the quantum nature of photon, so that's an interesting discussion. That's an interesting discussion on itself. Okay, we didn't go there yet. We didn't need that. What we have realized here is that we accomplished the main goal of this section to introduce the idea that quantum mechanical states are to be represented by vectors in an abstract complex vector space. All right. So this was our duty. Okay, this was our mission when we started with this Stern-Gerlach experiment. Our mission was to find some sort of mathematical framework that would describe the quantum mechanical systems. All right. So let me summarize what we have done so far, because from the next class we'll just dive into this mathematical formulation. Right? In this class, or in all these classes, what we have provided is just a motivation. Okay? We just we just provided the motivation to choose vector spaces to represent quantum mechanical systems. Okay, so let me just summarize the arguments that we have made so far. First class we discussed the double slit experiment. We discussed the double slit experiment, and there we saw that there's even if you send one electron at a time, there is an interference pattern being built up if you wait it for sufficiently long time. Okay, so from this we said that each electron passes through both slit, or basically each electron passes through both slits at the same time, or an electron can be at two different places, or many at different places at the same time. All right, now this we called as the principle of superposition. Now once we understood the principle of, or at least once we formulated the principle of superposition, we thought that, okay, what are the basic mathematical quantities, or what kind of quantities behave in the same way, and we said that these are vectors. All right, and we suggested that, okay, the usual three-dimensional vectors cannot be uh, sufficient, because each point in space is independent of each other, right? So we should have some sort of vector space with a large number of dimensions. Okay, so we said that there is a vector space, there is a mathematical framework like that, it's called the linear vector space, etc. And we suggested that quantum mechanical states can be represented by vectors in linear vector space. And then we developed, at least we gave the correspondence between nature and mathematics. We said that quantum mechanical states will be represented by vectors. Quantum mechanical observables will be represented by Hermitian operators, and the measured values will correspond to the eigenvalues, etc. Okay, that was one part of it. We made this correspondence between linear vector space and, or an abstract complex vector space, and quantum mechanical system by looking at the Stern-Gerlach experiment. That was the second part. By looking at the Stern-Gerlach experiments, okay, we saw something unusual, all right? But we made a correspondence with the case of polarization. Made a correspondence with the case of polarization of electromagnetic fields, or polarization vectors of electromagnetic fields. Okay, based on this polarization, we said that the spin states, okay, spin states, maybe they can be represented by some sort of abstract vectors. Abstract vectors, all right, because the basic behavior of spin states seems to be like the basic behavior of polarization vectors. All right, now we saw that, okay, let's develop some sort of vector space like that, but we see that it is not sufficient to talk about some real vector space. Okay, in order to make the correspondence complete, you have to talk about a complex vector space. we have to talk about a complex vector space. What do we mean by a complex vector space? This means that when we combine vectors, you can use complex numbers, right? You can use complex numbers to combine vectors. So usually when we combine vectors, when we write a vector is equal to ax x hat plus ay y hat, something like this. When we talk about something like this, these are real numbers. These are always real. This is a real vector space. Okay, but by pushing the analogy with polarization, we found that this is not sufficient. Right? We don't have enough. We don't have enough space if we are talking only about real numbers. So we make a generalization and we allow these to be also complex. We allow this to be also complex. Okay. So this is the motivation to choose basically, or at least you can consider this as a motivation to choose complex vector space as the correct mathematical framework for quantum mechanics. All right. Now I believe that this has provided you with sufficient motivation to study complex vector spaces. Complex vector spaces. Okay. So so understanding to manipulate these complex vector spaces is important to quantum mechanics. So this is the reason why from the next class we'll be studying complex vector spaces in detail.